possible with an instruction. As a result, every spatial check was combined with an LE. So if you eliminate spatial checks, we can reduce this overhead significantly. So in our latest implementation, when we have actually engineered the compiler to eliminate these inefficiencies, we have reduced the overhead to about 10 to 15%. So by adding these new instructions, we have reduced the overhead from 180% extra instructions to just 81% on an average. Now you may ask this question, you said 29% overhead, but now you are saying the instruction overhead is 81%. Why are we not seeing why you are executing 81% more instructions, but we are seeing just 29% overhead? This is because your processor has a lot more ILP than your program can actually use it. So if you look at your Sandy Bridge machine, it executes 6 instructions every cycle, but your program does not have the capacity to execute 6 instructions. Most programs have an ILP of 1.5 to 2. So since we added these extra instructions, these don't depend on the other instructions, they executed for free. They're executed for free. As a result, even though we have larger instruction overhead, your performance overheads are a lot less. Okay, so by having by eliminating spatial checks, having aggressive spatial check optimizations, we can eliminate spatial checks, and by hacking the code generator, we can eliminate LEAs. So currently, our instruction overheads are about 40%, and our runtime overheads are about 10 to 15%. So from 2x what we had earlier. Yes.
So these black bars still look pretty big to me.
So the other, so this is an interesting observation. So there is another component. So these are instructions which are neither are instructions or not LEA. So one of the things you need to do when you make a function call is you need to propagate the metadata for the pointer. Let's say you have a function food which takes a pointer as an argument. How do you propagate the metadata? So one suggestion which Intel NPX has done is change the calling convention, and let's have extra registers in the ISA which are used to propagate the metadata. On the other hand, for this research, we use shadow stack, which mirrors the actual execution stack. Now we need to perform extra loads and stores for the shadow stack, which account for this other instruction. If you are willing to change the calling convention, which we are, but just that you have to change the entire tool chain, unless there is an industrial pressure to do this, most people are not willing to do that. So we just report results for the instrumentation without with the shadow stack, without using the extra registers. So that's a good observation. Okay, so now what we are saying till now, in the next like 10, how much time do I have? Like 10 minutes?
10 minutes, is that enough time?
Yeah, I'll probably take five more minutes. So what I've been what I've been advocating till now is use compilers. That's because I'm a compilers researcher. But use compilers. Compilers have lots of information. But how do you say compilers are correct? So what we said was do the memory safety transformation within a compiler. Now, how do you say this transformation is correct? So you need some semantics for IR to do the transformation. Because as with anyone, you design an algorithm, you say the algorithm is correct, right? But it says nothing about the implementation. So what we proved as researchers in our papers was the abstract specification of the algorithm is correct. So if you do this, you do the correct thing. But we wanted to do something much more significant. We wanted to say, one thing is, Santosh implements compiler optimizations correctly, so he should be doing the right thing. That's one way to go about doing this. Alternatively, we want to say, this optimization or this transformation is proven to be correct mathematically. So how do we do this? This was the research question which motivated us to design a transformation which is correct by construction. Then we realized this is a compiler optimization. This problem is analogous to. It's interesting.
All right, well, we'll call back.
So this transformation, what we are trying to say, building a transformation correct by construction is analogous to saying, can we trust the implementation of the compiler? Okay, so but compilers are used by thousands of people, right? Everyone uses GCC. Like most people don't know what goes on inside GCC, but still everyone uses. Compiler should be robust. So, and now it's just is it just a question of trusting Santosh's implementation of memory safety transformation? And there was a nice paper in PLDI 2011 by John Rigger's group. They surveyed a large number of industrial strength compilers, GCC, LLVM, ICC, Open64, and many others. And all they did was a simple task. They generated random valid C programs. So these are valid according to the C specification. They are random. So the programs, they do something. And they tested it with these compilers on a cluster for some time. And these compilers have been used for a long time. And these are in the main trunk. They are committed. And they found lots of bugs. Okay?
How large?
These programs are 10. Again, C Smith is a tool. It generates about programs that are about 10 instructions to 20 instructions. And there are larger programs which are permutations of these and compositions of these. So there were two kinds of bugs that these guys found. One was the compiler crashes. Okay? And the second kind was compiler produces wrong code. So among these two bugs, the first bug is okay according to me. What does it mean? You have a favorite C++ program and you cannot compile it with GCC or LLVM. Who cares, right? But the second bug is much more serious. Let's say you have a compiler. It's silently producing wrong code. And your test harness is not good enough. And this wrong code gets into production. And let's say this is part of some avionics system. And instead of decelerating, it accelerates. Imagine the consequences. So this is a serious bug, and people have looked at it. If you ask, if you have listened to Tony Hoare and the grand challenge of computer verification, he says verifying a compiler is a feat of its own. One of the impressive pieces of work in the last decade has been Concert Compiler, a completely verified end-to-end compiler for a subset of the C language from Xavier Loa's group in India. So we were impressed by this work. And we wanted to do something similar for our memory safety transformation. So this was for the custom file languages, custom front ends and back ends. So we wanted to do this for LLVM. So we don't have the luxury of redefining everything in LLVM. We talk to LLVM developers, we get their feedback and stuff, but we cannot change everything. So we still need to interoperate. That's a fact of modern software, right? So can we do anything about it? To address this, we formalize the semantics of the LLVM compiler. And then we built various facilities for creating proofs. And then we realized writing proofs in a proof assistant, like I don't know how many of you have used proof assistant, but if you have used a proof assistant, writing proofs and implementations in a proof assistant can be difficult for people. So we have created various facilities to ease this job. And then it takes time to write optimizations, right? We surveyed all the optimizations and we found out there's one optimization in the LLVM suite which gives you 95% of O3. One optimization gives you 95% of all the other optimizations. This optimization is known as mem-to-reg. And we set out, let's actually build this mem-to-reg optimization correct by construction. And this was a side project, although our goal was to prove that the memory safety transformation is correct. And what I'm going to show is a brief proof sketch of how we are going to show that the memory safety transformation is indeed correct. So just to give you some challenges, since I just have 5 minutes. So what are the challenges in building a verified computer? Verified LLVM. The first challenge was the semantics of LLVM compiler is a series of English documentation. And English as such is ambiguous, and when you have multiple programmers putting in something together, it's all the more ambiguous. And this entailed us to reverse engineer the semantics, talk to the developers through the mailing list, and understand the stuff. Okay, so one of the key contributions of our work was there is a feature in LLVM called as Undefined. So LLVM wants to be aggressive in the presence of undefined behaviors. For example, let's say you have an operation, you're shifting by x. Okay? You have an operand, an integer operand a, and you're shifting by x. And now, if the compiler proves this x is greater than the width of the integer, the compiler can do anything with it, because this program is undefined when the width of when x is greater than 32 for an integer. So there are lots of such undefined behaviors, and compilers assume people write correct programs. They don't compile for wrong programs written by various people. So compilers are aggressive. So and LLVM wants to be aggressive because all it wants to do is specify the language specification, and it's aggressive. So it has an undef feature, and there are like lots of developers in LLVM. Most of them did not know the semantics of LLVM, and we showed that the semantics of undef is actually collecting semantics. Each undef is a set of values, not a single value. And if you read our Popper and PLDI, Popper 2012 and PLDI 2013 papers, you'll find more details, but I'm not going to go into detail due to time constraints. So the other contribution of our work was the proof technique for reasoning about SSA. SSA, everyone knows. If you take a compiler's course, what SSA is. But how do you write a proof for SSA optimization? This was not known, but we had a simple technique which can be used to prove the correctness of various SSA optimizations. So due to time constraints, I'll skip through the various aspects of. Okay. So essentially what we are trying to do while writing the memory safety transformation correct by construction is we are defining a partiality in the semantics. So your program can get, like let's say you're defining a state machine to say this is how the program gets executed in the abstract state machine. And there are various ways your program can get stuck. And one of the ways it can get stuck is by a predicate called the memory safety violation. And what you are trying to do is, let's say you have a program, S1, and the program is well formed according to the C language, and then you run the transformation, memory safety transformation. In this call, I'm calling it as softform, and you get a resultant program. You're getting a resultant program S2. So what we are saying, the first claim we are trying to make is there is no spatial memory violation in S2. And then this original program and the transform soft mode program, transform memory safe program are equivalent. This is the refinement relation that you need to prove. So again, the details are not important. What we have essentially done with the semantics is we have written the memory safety transformation and the proof in a single ecosystem. The ecosystem is known as the cock proof assistant. So once we do this, we can extract an implementation that comes with a proof of correctness. And we have generated an implementation which is verified that the implementation comes with a proof of correctness. So, and this implementation actually interoperates with the entire ecosystem. So again, we have also written various other optimizations and various facilities to do this. Okay, so to conclude, what I have shown you today is providing comprehensive memory safety is not hard. Like I talked to a lot of developers, and I've been talking to various C programmers. There are two extremes. People say C can never be made safe, and others say, making C programs memory safe has extreme overhead. Both views are, in some sense, not grounded in truth. So you can really make C programs to be safe with the help of the compiler. Leverage the compiler. That's the key message. And when you leverage the compiler, you can keep the hardware investments nominal. You don't need fancy hardware. And the other thing what we have realized is since we leverage the compiler, your compiler needs to be correct. So we have proposed some mechanisms to build compilers correct by construction. We think this would be a foundation for building verified systems. So for all those who got excited, and if you want to try out the memory safety transformation, it's available from my GitHub account. I maintain it daily. And if you have suggestions for improvements, or if there is a case which is not being handled, let us know. And thank you for your attention.
So did you prove that the memory safety transformation is correct, or did you generate a proof generator that proves that the resulting code is memory safe?
No, so we proved that the memory safety transformation is correct according to the abstract specification of the memory transformation type.
So you couldn't use this to build, or could you use it to build like a proof carrying code where I can download code and jump to that?
So there are various aspects to it. One way to do this is proof carrying code. That's when you want a third party to verify your proof, but that was not our focus here. Our focus here was to show that the implementation actually satisfies the specification. And in fact, to our surprise, we discovered many bugs in our memory safety implementation. Even though our algorithm was correct, had just missed out so many corner cases, which when we actually did the proofs, we couldn't prove it correct. Then when we actually reasoned about it, we figured out, oh, this was a mistake in our implementation. So this shows the value of writing things correct by construction.
So your main objective, I think you mentioned this, is to have a safety of the system, critical, right? Where safety is critical. What about situations where safety is not necessarily critical? Right? I have a code, that I've written, and I may have some issues with memory. Could your system help me improve my program? In other words, once it sort of, it may tell me, you're assigning, you're breaking you're not reading what you should be reading. I go back, modify my program, try it again, write that.
So for example, there are two answers to your question. One, safety critical. What is safety critical? This definition changes over time. So for example, the security of your system is defined by the security of the weakest component in your system. And for example, people never thought like the use of retrieve would be a security vulnerability. And if you leave a hole, people catch on it. And now, what we want is, there are two aspects to it. One is building code that is robust, building systems that is robust. And other is providing mechanisms to programmers to build them. So by having this checking integrated as part of your testing stages, it raises the exception precisely at the point where the exception occurs. Now the programmer can easily fix this. Instead of allowing the program to corrupt memory and then relying on your memory allocator crashing.
That's right. Usually what happens. That's right. Especially simulator.
So this is instead of using a simulator, you have a precise system which will raise an exception right there. So the whole philosophy, what we are trying to do is provide tools, make it easier for programmers to build systems correct by construction at various levels.
What is your notion of program equivalence?
So here the program equivalence notion, we have a refinement relation. So what we say is you have your original program and it has a set of behaviors. Let's say the set of behaviors is yes, and you have an optimization and it refines the behaviors. You get let's say the resultant set of behaviors in the optimized program is S dash. S dash is a subset of S. And now, depending on the optimization, you need to come up with this refinement relation.
So that's not really equivalent.
So it's not equivalent. Like it's only the observable states are equivalent. So again, if you have like let's say A equal to 5, A is dead code, it's not necessary for the dead code to be equivalent, right? What is observable is equivalent.
No, I understand, but it's still not. We can talk offline.
Oh yeah, sure.
I guess I want to ask you something a little bit radical. I mean, how many people these days, or what classes of people really, does it really make a difference for about the 2x versus the 2x overhead? I mean, most of the programs I write, I don't care. I'd be happy to spend 2x overhead to avoid getting into these problems. I wouldn't want to tie myself in knots just to avoid that. So, but I mean, there seem to be a lot of people that still care about this. So,
They do. So there, like for example, let's say you're building. Let's say you have a runtime that's providing, that's a face recognition library, and it means that your response time slows down by 2x. So these people care about it. So that's why there are applications, HPC applications, where 2x means like your simulation is running for 24 hours, now it's going to take 2 days.
Perhaps these things, though, are not the ones that are gonna be attacked by the, if through overflow attacks, I mean, you'd be more concerned about your web.
So the browser is like one key component, right? So browser, for example, if you talk to browser developers, they care about performance and real-time response to user queries, and 2x is still a significant amount there. So this is, again, one thing that has changed is there were none of the tools which provided 2x overheads. Like the tools which were robust enough to run in deployment were like 10x or 20x. Now Valgrind was the tool which is commonly used, it's about 20x. And doing anything 20x is not feasible. So, but with 2x, you can actually deploy things and test it. And many of them, like for example, Java slows down the program by 3x. So people, in many cases, people do use Java and Java-based systems. Right? And below this is discounting the garbage collection overheads of Java. So what we realized is many of these checks are so much coupled with the actual execution. So parallelizing is, again, it may be useful in some context, but like you need something similar to fine-grained parallelism, which can parallelize at a very fine granularity rather than at a coarser granularity. So, but amortizing the overheads with parallelism is a research challenge of its own.
So if the programmer were willing to annotate the code, how much better do you think you can get the overhead?
Programmer is willing to
Annotate the code.
So again, if programmer is willing to annotate the code, we can get it to like 5%. Like for example, one of the impressive pieces of work in this line of work is deputy from the George Nicholas group at Berkeley. So this is essentially a refinement-based type system where the programmer says this is the range of values and this is the bound of this array in some places, and the system just checks it. And in those cases, you can actually reduce the overhead significantly. And so again, we have been focused on the programmer does not want to take any initiative about fixing the code, and we still want safe systems. And what is the lowest we can do in setting that?
That was my question for you. You sound like you're using sort of off-the-shelf optimizations. You didn't have any special. You didn't add any optimizations that understood the semantics of these bounce checks.
So we didn't do any optimization. So like there are many other optimizations which can be done. For example, Vikram's group at Illinois has a suite of optimizations just proposed for memory safety. All those can be applied. But again, since we are already at 15 to 20%, like it's diminishing returns, but those are useful. Okay, any more questions? Yes.
This study was scalable to multiple threading?
Yes, so that's a great question. So how do these scale to threading? And so again, it's pretty straightforward. So there's a preliminary implementation that we have that works with multi-threaded code. So the key thing you need to ensure is atomicity of the metadata access and the pointer load. Whenever you load a pointer, you're also touching the disjointed data space, and you need to enforce the atomicity. And if your code, like there are two cases, if your code is database free according to the language specification, then all these checks are atomic by definition. But when you have races, you need to add extra synchronization to ensure the atomicity. And the other thing you need to be aware of when you're threading this, when you're using this checking in a multi-threaded context is you need to use thread local identifiers for the identifier allocation. So there is a nice memory allocator called hold from Emery Burger's group, and which is widely used. If you use an Apple system, that's the default allocator. So the key idea is each thread uses thread local pools. They communicate with the global pool only when they are exhausted the thread local pool. You need to do the same thing for identifier allocation.
Okay. Thank our speaker again. And people can chat for a minute, although I think there's going to be CSGSC elections